Okay, so what questions do you have? What's on the test? Yes, okay. So actually, let me talk about that for a second. A good way to prepare is to go through the pictures you have of your exams, okay? So I've gone through the previous exams and I've looked at all of those sort of application questions and the creative questions, and I kind of mixed them together. And what I've done is, instead of giving you optional problems to do, I've given you optional things within the question, like draw a molecule with a mirror plane, right? So you get to pick your molecule. You know, so there's choice built into the question, creativity built into the question. So there's not like a section of questions that are creativity questions. There's 20 vocabulary sentences, and so you need to know those vocabulary words from the Quizlets. And it's a sentence with a blank in it. So you got to know what word goes in the blank. And I tried to pick. This took me about 4 hours yesterday. So hopefully, you don't have to appreciate it, but I hope you do. So I was going through the Quizlets, and I took those like 97 words and 40 words and 50 words. I mean, it was like 250 words. And I went through and I made a top 10 list out of each one of those. And so I would encourage you to do the same. Like, go through those and say, which one of these words did DW use 20 or 30 times during a semester? You know? And that'll help you figure out which ones are probably going to be on the test. Okay? Millikan notation, how many times have I said that? That's going to be on there, you know? That's what I'm talking about. When you're looking through this and you see predissociation, how many times did I talk about predissociation? I mean, yeah, it's a vocabulary word, but is it a top 10? No, it's not. So those kinds of things, you should be able to prioritize. And to me, that's the learning process. The final isn't just me trying to test you and trick you and figure out what you know. Your prep for the final is learning. So this exercise that you're looking at the vocabulary one more time and going through it and saying, yeah, that's a top 10, that's a top 10, that's a top 10. And you may miss me. I may say this one's a top 10 and this one's not. And we missed that, but it's worth 2 points. Okay? Or if you're looking at it and I'm thinking, the word is Jablonski diagram and you put potential energy surface, that's pretty close. I might give you 1 point for that. You know, so go ahead and put your best effort on that question, even if it, you think, well, I don't know, I'm going to write something. Okay, so write something in those blanks. Then there'll be 6 problems. That sounds like a lot, but I want 40% for the vocab, and then 6 problems that are 10 points apiece. Okay, so you have lots of opportunities for points. Each one of the little items on all those problems is about 2 to 4 points. So any one little item is, it's not all or nothing. So you got a full page to do this, do the transition equation for the rotational energy equation for delta J plus 3, okay, or something like that, right? You need to be able to do the transition equation. If you got the transition equation, can you predict what the spectrum would look like? Are they peaks equally spaced, and those kinds of things. So think about that. That's one from the first exam. Things from the second exam, third exam. So just go through those pictures that you have, and since it's not a direct copy of that problem, don't worry about if you missed something. I got to get the answer for that one. Try to track me down because I've got 5 deadlines going right now simultaneously. So I'm going to be hard to find. I've also got stuff this afternoon with the band, the high school band, you can see. And so I'm going to be gone after 3. So it'll be hard to get me. So don't get worried about trying to find me and find the key for any of those previous exams. But look at those problems and study those concepts. Okay, and that'll be a good way to prepare. Because I like to have you guys have a good target to aim at. Okay, so with that sort of introduction, I'll open the floor for questions. Yeah, what's up, Don? Oh, I said I wasn't going to use names. All right, go for it.
So, since you just mentioned the transition energy equation, could you go over an example of that?
Yeah, sure. So whenever we have if you hear transition equation, that's telling us where the lines show up in the spectrum, right? And so the lines in the spectrum are differences in energy levels. So we need to find the energy level equation. So we have a spectrum, it has a peak, that peak is a line. That peak is a difference between two energy levels, and that energy levels have an equation that's associated with them. And the equations that we looked at were the particle in a box, particle on a ring or a rotational motion, so the rotational energy equation. For a diatomic, we looked at it for a diatomic, which had the rotational constant. And then we had vibration. So those were the three energy equations that we had. For the MO diagram, I mean, there's an equation for those energy levels, but we need Gaussian to give us that. There's really no easy way to come up with the electronic energy equation. But for rotation, vibration, and translation, we have three energy equations for that. So let me back up and start with those three equations, okay? And you guys are, studying all this material all the time and eating, drinking, and sleeping it. So if I get stuck on these energy equations, I want you guys to help me out, okay? So let's start out with the particle in a box energy equation. That's the first one that we talked about. First of all, what's the quantum number that we used for translational motion or the particle in a box? What's the quantum number? N, yeah, so I'm going to put that down here just to kind of show that that's the quantum number. So E with the little subscript N is equal to, it was N, was it N or N squared? So this is just the energy equation, not the transition equation. Anyway, what do you think is on top and on bottom? It's way back there, isn't it? This is September we're talking. Yeah. It's N squared. And then what else? It's dot, 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 dot. So there's 5 pieces to it. H, yeah, okay, well, you can do it with H bar. Let's do it with H. 8 M L squared. Okay, so this is the length of the box. That's the mass of the particle in the box. Right, so we have the particle in the box wave functions that give us this energy equation when we do the Schrodinger equation on it. Planck's constant and the quantum number. And 8. Okay, so that's the energy equation for the particle in a box. The 1D PB. So for rotation, what was the quantum number that we used for rotation? Think about the carbon monoxide lab. J, yeah. So we'll put a J there. So what does this equation look like? Review is tough. Yeah. So since this is rotation, what are some things that I can think about in terms of the energy? We had some constants. We have constants up here, H and 8 and so on. Are there any constants in the rotational energy equation? It's so obvious I don't want to say it. What? Well, pi is inside this constant. Yeah. B. And what is B called? The rotational constant. Yeah, so we had the rotational constant, B, and then it's times the quantum number plus 1. B times J plus 1. So that's the energy equation for the rotation with the rotational constant in front. So we lumped all this stuff about rotation into that B constant. And so that's a rigid rotor. Yeah, we're like, what's rigid rotor on that? What was that caused everybody to ask about that? Oh, the ACS exam. Yeah. Yeah, we're like, what in the heck is that? We never covered that. Bing! What does this mean by rigid rotor? Well, it means it's a fixed bond length and it just spins. Okay. If we added the extra pieces like centrifugal distortion where it stretches, then we're breaking the rigid part of the rigid rotor. Okay. So this is a rigid rotor energy equation. Let's go ahead and write B. Now this one I need some help on, so find this in your notes. I know in the denominator it's got mu r squared. That's how it depends upon the reduced mass and the bond length. Okay, this is for a diatomic that we're talking about. But it's got some other stuff in here, so where are my constants? You have your notes with you? What's on top? H? All right. Not squared or anything like that, so H.
And then on the bottom it's 8 pi squared C.
Okay, 8 pi squared and C. Okay, but those are all constants. The real issue is it's 1 over mu and 1 over r squared. So it depends upon r squared in the denominator and the mass of the particles, the reduced mass. And mu is equal to m1, m2 over m1 plus m2 for a diatomic. So that's the rotational energy equation, but notice how you've got this simple little rotational constant, B, and then B is related to mu and R, and mu is related to the masses of the particles. Okay, so it's just sort of nested in there. Okay.
Are the units weird for
What's that?
Are the units weird for the
Yeah, so if we wanted, let me do this. I'm going to put a little tilde up here. And what am I doing when I put that little tilde on these things?
Wave numbers.
Yeah, that's indicating that it's in wave numbers, okay? And so we need to use the units that will convert everything over to wave numbers. And 'cause that's going to be convenient when we're dealing with infrared spectroscopy and the x-axis is in wave numbers, we would want our B to be in wave numbers. So when we take differences between the energy levels, we end up with some multiple of B, like 2B and 4B. Okay. So this is, and so then we want our masses, and so we could take this, remember I said that note card bait, which I was really sad, there were several people on this test that did not utilize that slide where it says make life easy for yourself. All of these constants you can change, and it's like 16, does anybody have that constant handy on their notes that they found?
16.85763?
There you go, 0.8, we'll go to 8.6, right? 16.86. And the units were wave numbers. Let's see, grams per mole, angstrom squared, right? So this the units. Angstrom squared will cancel with my bond length in angstroms. Grams per mole will cancel with my reduced mass, and that allows me to use my masses right off the periodic table. I don't have to convert things to kilograms. So that's why this constant is so nice. Otherwise, I'd have to convert these to kilograms and work on with joules and then convert joules to wave numbers, and it's just a big mess. And then the wave numbers is what comes out on top. Okay. So this is a nice constant to use to get bond lengths and reduce masses. Okay, so this is all wrapped into B. Can we see that on the video? Yeah, we can. Okay, and then there's one more energy equation that we had. So this was translational motion, or a particle in a box. This was rotational motion of a rigid rotor, just a mass moving around a fixed radius. Okay.
Vibrational.
Vibration. So E tilde, what's the quantum number for vibration? V. Yeah? I thought you said something. I don't want to rush you, but we got to move. And speak up when you find something.
HC nu times V plus V.
Yes, okay. HC nu plus V. Yeah. So you need the HC when you're converting it over to joules. And so if you just leave it at nu tilde, then it's in wave numbers. Okay? times V plus 1/2. Okay, and so that, because it's just V plus 1/2, and there's no squares or cubes or anything like that, that's the harmonic oscillator. This was rigid rotor. This is the harmonic oscillator. The energy equation for a harmonic oscillator. Okay, they're equally spaced. As I go up in V, it's linear in V, right? It's V to the first power. And so those energy levels are equally spaced. What's the spacing? If I go from V equals 1 to V equals 2, how much has it increased? The vibrational frequency. So the vibrational frequency is also the spacing in the energy levels. What about this? This is not equally spaced. It's J times J plus 1. It goes as J squared. So J equals 1 to 2 is a small spacing. J equals 2 to 3 is a bigger spacing. 3 to 4 is even bigger, and so on, because it goes up as J squared. What about this one? N squared. It's not linear space. So all of these top two go up as the square of the quantum number, but vibrational frequencies in the harmonic oscillator just go up linearly. They're just equal space. We call it equal ladder of states. It's like the rungs on a ladder, because this would make a crappy ladder. Right? You one space, you get one up rung, two rungs, and then the third one is going up by the square. You couldn't climb very high on that ladder. Okay, but an equal ladder of states is what we call the vibrational energy equation for the harmonic oscillator. Now, this vibrational frequency also has a mass dependence. So what is that equation? How do we relate frequency to mass?
1 over 2 pi c, and the whole thing times the square root of kf over mu.
Yes. All right, so that's the frequency equation that relates it to the mass. And what do we see in all of these cases? This is something to point out. Where's mass? Okay, look at that. Mass, he's here in the denominator. In here, in B, the denominator. Here, vibrational frequency, denominator. So when the system gets bigger, heavier, the energy levels crush down together. So the vibrational frequency for a big set of masses is going to be really low, and one for like hydrogen, H2, is going to be really high, a high vibrational frequency. So as the mass goes low, the vibrational frequency goes high. As the mass goes low in rotation, then the difference between the rotational energies gets further and further apart. And the same with the translation. As the mass gets small, the energy levels get further apart. It's a smooth transition from atomic masses to macroscopic masses. There's no dividing point. As you get smoother in the periodic table, as you go higher and higher and higher, let's just think about the diatomics: fluorine, chlorine, bromine, iodine. You know, the fluorine vibrational frequency is pretty high, but when you get to iodine, we did that lab. What was the vibrational frequency for iodine? You did a table, you had the Dislanders table, you had all of those numbers, and it was nu E double prime. Give me an order of magnitude. Was it 10,000 wave numbers, 1,000 wave numbers, 100 wave numbers, 10 wave numbers? Any idea? Retention is so tough. That's the number one problem in education, is retaining what you've done. Yeah. It's not 10,000, so take that one off the table. It's not 10. It was 214 wave numbers for iodine. What's the CH stretch vibrational frequency? This one you ought to know from organic. You've had several tests on this. CH stretch in wave numbers. The vibrational frequency for that CH. So in your infrared spectrum, you see some peaks over there. Where do they show up for the CH stretching? Huh? Speak up. Come on. What about a carbonyl? 1600-ish, yes. So carbon oxygen, 1600, that's the vibrational frequency. So that's related to the masses and the force constant. Carbonyls have a double bond. So the force constant goes up, higher frequency. Carbon oxygen with a single bond is about 1100 or 10 or 1000. So when you add the double bond, it goes up to 1600. CH stretch, that tiny little mass, single bond, is about 3000. Okay. So these are our energy equations. Now pick one and we'll do a transition equation. Rotation. Okay, very good. I was hoping you wouldn't pick the vibration because it's so easy. It's just the transition equation is just the vibrational frequency. I'm going to scoop this up. Is that a good color? Can't tell. Let me zoom in. This is terrible. I mean, it's a good camera, but it's just so bright in here, it's not picking up anything. All right, let's go with that. Okay, so give me a delta J. So let's say we do the selection rules, we analyze everything, and we say, okay, the selection rules tell us that a particular change in quantum number is allowed. Okay. So if you had to pick a delta J, just pick one. Someone. +3. Okay, so we've determined for some kind of crazy, like Sam Houston spectroscopy method, delta J equals +3. So that's our selection rule. For SAM spec, whatever that is. It's some kind of triple thing because we got 3 units of angular momentum going on here. So the 3-photon process, SAM spec gives us a selection rule for rotation of +3. Okay, so how do we use these two pieces of information to come up with the transition equation? You've got to know how to start the problem. Say that again? You're on the right track. Go ahead. Well, we could, but let's just leave it in terms of B. Like remember when we did our peaks in infrared, like R branch and P branch, the spacing we said that it was spaced by 2B. And then so the difference in frequency in that spectrum was 2B spacing, and we could then pull that out and then look for bond lengths and angles. Yeah, it was like the Hamlet deal. With Raman was 4B spacing between the O branch lines and the S branch lines, and then the P branch and R branch lines in infrared were 2B spacing. So if I just have two of those lines, I can take the difference in frequencies, divide by 2, and that's B. Now I know B, I can solve for the bond length. Or if I know the bond length, I could solve for the masses. Right? Okay, so but what do we do with this selection rule and the energy equation? Yes?
First you substitute in for J +3.
Yes, so we're looking at differences in energy levels. So we have these energy levels, and we're looking at this delta J of 3. So we need E of J +3 subtracting E of J. So E of J +3 subtracting E of J, and we'll do it algebraically so we get all of them. Okay, so we just write out this equation, E of J +3 minus E of J is equal to delta E, and I'll go ahead and put +3 in the subscript. So I've got this difference of E for the +3 selection rule is J +3 minus J. And so that's essentially the transition equation, but it's not simplified. But this is what we're talking about. This is a spectroscopic transition, and we have an equation for that. We take the energy equation and we put in the selection rule into the energy equation and then algebraically clean things up. So we'll try to go quickly So we have B times J plus 3 times J plus 3 plus 1. Does everybody understand what I did there? Why I'm leaving this plus 3 and plus 1? Just to make it clear. That's all of the, wherever there's a J, I put in a J plus 3, and then subtract B times J plus 1. And then we're off to the races. We're just going to have to multiply everything through. I'm going to go ahead and pull the B out of everything. So I've got the B's here. I have a J squared from the J here. So FOIL first, you know, what is it, outside. So then I've got J times, and this is 4 over here, plus 4J inside. Okay, I've got J times 3. And then outside, I've got 3 times 4. So that's this first one, expanded. And now I subtract all of these. I've got a minus J squared, and then a minus J, right? Because it's minus J times 1 minus J times J. Everybody cool with that? So there's our algebra. Then we just simplify things. Our J squareds are gone. Okay. We keep the 12, but I've got plus 7 minus 1, so I've got 6. So I have B times 6J plus 12. And that's, you could leave it like that, or you could go one step further and you could say it's equal to 6B times J plus 2. And the reason I like this one is because that's the spacing between my spectral lines. So I'm going to have a spectrum, and I'm going to label those lines with my J quantum number, and I'm going to have a J 0 to 3. So I'm going to label that whatever, you know, J0, and then the J1 will be the 1 to 4. And the difference between those in the spectrum will be 6 times the rotational constant. Because that's the difference between J equals 0 and J equals 1. And then J equals 2 will be another 6B. So it's going to be, the spectral lines are going to be looking like this. So in the spectrum, they'll be equally spaced. And the difference here will be 6B. And this might be 0 and 1 and 2 if we label those by J. So let me zoom in on that. So this would be the simulated spectrum. Anybody got that? So because my transition equation is 6B times J plus 2, I would have a spectrum down there that has equally spaced spectral lines. And if I take the difference in those spectral lines, I can solve for the rotational constant. Once I have that, I know how mass and bond length are related. If it's a diatomic, I can solve for it right away. If it's not a diatomic, it's much more involved, but you know, that's how we solve for the structure of small molecules for years, using rotation and vibrational spectroscopy. So that's an example of that one. I saw your eyes kind of get wide when I said, you know, here's an energy equation, here's the selection rule, come up with the transition equation and a little simulated spectrum. So it's not too bad. This is a simulated spectrum, right? If I wanted to label it even more, I might say, well, the intensities, you know, were related to J prime, you know, light, and J double prime, okay, squared, you know, just to kind of show there's an intensity. I know what the intensities are from, too. I won't have the numbers for those, but I could at least label, you know, what I would say about them. So, you know, okay, we could beat that one down. So, yes.
I have a question about that. Isn't the spacing between them 2B each? So like 0 to 3 would add up to 6B, but the individual spacing is 2B?
Let's think about it here. If I go from, if I put 0 in here, okay, then it's 12B. If I put 1 in there, then it's 3 times 6 is 18B. And so the difference between 12 and 18 is 6. And so what this really is this is some sort of, from here, this is 12. This is 18. This would be 24. Okay, and so they're shifted from this point by this transition equation. But if we look at the difference between those ones, this is the difference between them, because we pulled this piece out, and that piece is the spacing between the lines. Does that help?
Where does the 2B come from then? Because you said like the IR and the difference in the spacing between.
Oh, the IR, it comes from the selection rule. So in IR, in the row vibrational transitions, we have a selection rule of delta J plus 1. Okay, and when you put plus 1 in here and you solve for things, then a 2B comes out. And then in Raman, we have a different selection rule of plus 2. And when you put the plus 2 in here and do the transition equation, then a 4B comes out. We did a plus 3, and so that's where the 6B came from. And it does look like a trend. Whatever your selection rule is, it's going to be twice that selection rule for the number of B's that come out. Yeah. Okay. So, but I wouldn't want to bank on that. I'd still do the algebra. Right? But it's going to work out to where it is for just for rigid rotor rotation. Those selection rules are going to give us the spacing in the B's. Yeah. Nine minutes. Yes.
So I was doing one of the debates, and the question was, what is it required for molecules to display rotational lines and vibrational spectra? The answer was gas phase sample.
Oh, yeah.
I was wondering if you could explain.
Okay, so in the infrared spectrum, if we want to see rotational lines, they have to be freely rotating. And so the only way you're going to get a freely rotating molecule is in the gas phase. So if it's in the liquid phase, they'll try to rotate, but they'll bump against their neighbors. In the solid, they're fixed. And so that's the answer. Now, what's required for, that's in the infrared spectrum. What about in the microwave spectrum? So now we're in a pure rotational region. So the only thing we're trying to do is rotate the molecule. We're not vibrating it.
A net dipole.
A permanent dipole, a net dipole. So the molecule has to be polar. It doesn't just have to have polar bonds. Like BH3 or BF3 is symmetric. And so the boron-fluorine bonds, they have dipoles on them, but they're symmetrically positioned around the boron. And so that has a no net dipole, and it will not feature a pure rotational spectrum. If we put it in the IR, it can vibrate and rotate. That's the row vibrational, and we can do that because some of those vibrations break the symmetry. And since they break the symmetry, then you can have rotation and vibration, together. But nitrogen gas and oxygen gas, both very symmetric molecules, they're not going to feature a pure rotational spectrum. So that's what makes them not a greenhouse gas. So the light hits us from the sun, the visible light and UV light and everything gets kind of percolated down into the radio frequency, and there's clear windows in the atmosphere for that energy to leave the Earth in the radio frequency and microwave region. If nitrogen and oxygen were greenhouse gases, we wouldn't have an atmosphere because it would have boiled away our atmosphere. It would have heated up the atmosphere enough that it would have eventually had an escape velocity and left. So it's a wonderful thing that we have d infinity H molecules surrounding our planet. Okay, because a d infinity H molecule does not have a net dipole. Okay, but carbon monoxide, water, and CO2, because it's a polyatomic, can do row vibration. Those are greenhouse gases. Anything basically that's got vibration and rotation manifolds can absorb in that radio frequency range. Okay. Yes. Okay, which one?
This is option 2.
Okay, let me see. I've got them all here. Make sure I don't click the wrong exam. Finals in here too. There's the final. Voila. Wait, where'd I go? Let me switch this over. Option 2.
Oh, on the next page, please.
Okay. This one?
No, it's like an Excel has.
That's the one with these the little matrix elements?
Yes.
Okay, yeah. These guys?
Yeah.
Okay. So let me see what the question is actually asking. Zoom out. Golly, I kind of chopped the exam up. Let me pull up the exam without it being chopped and zoomed. Okay. Oops, too far. Okay, option 2, yes. So we're looking at this, these two results. This is from the particle in a box spreadsheet that you guys worked on in the lab. And it was saying that the student said the wave functions are not orthonormal. And the student said the selection rules for absorption and emission, and this is particle in a box, were plus or minus 1, plus or minus 3, and plus or minus 5. Just like the 1D particle in a box. So this is some particle in a ring problem. And so here are the matrices. Critique what the student got right and what the student got wrong. So be specific to justify your claims. So which one of these, left or right, tells me about orthonormality? And you can look at the designations here. These are the Dirac notations. So this one on the left has psi times psi integrated over all space. And the one on the right has psi x psi integrated over all space and squared. Which one of those tells me about orthonormality? The one on the left. Very good. Good, strong response. And now looking at this one on the left, what do we see in terms of the pattern? These are the results of the integrals of psi times psi. Yes, if it's times itself, it's 1, and if it's not times itself, it's 0. That is orthonormal. Orthogonal when it's times something else, and normal when it's times itself. And there's that question that we had last time that confused everybody. You thought the normal mode of vibration was top row. That's not what normal means, okay? Normal means normalized. And so a normal mode of vibration just means one of the normalized vibrational wave functions. How many does a molecule have? How many normal modes of vibration does a molecule have? How many total degrees of freedom does a molecule have? 3n. Number of atoms times 3. X, Y, Z for every atom. Okay? How many of those are translations? 3. The whole thing moves in X, Y, and Z. Okay? How many rotations does a molecule have? Nonlinear. 3. This can spin, it can do a forward roll, and it can do a cartwheel. I'm not going to do that today. Now what's left? 3n minus 6. Those are vibrations. 3n minus the translations minus the rotations are vibrations. So 3n minus 6 for a nonlinear molecule is the number of vibrations, and there's that many normal modes, that many vibrational wave functions. Okay. Now go to the right over here. The student said that the selection rules are plus or minus 1, plus or minus 3, and plus or minus 5. What do you see?
It should just be plus or minus 1.
Yeah, the off-diagonal elements are only plus or minus 1. So how do I figure this out? Let's say I pick this one, n equals 2. And I go over here and it's going to 1, which is a minus 1, and I'm just going over here to 3, which is a plus 1. So from 2 to 1 and 2 to 3, those are allowed. but no others are allowed. So the student was right about the plus or minus 1 and wrong about the 3 and the 5. And so that's really the answer for this one. So did that help, Jack? Jerry? Yeah. Okay, fantastic. We are out of time, but like I said, go through these tests and study these concepts, and it's going to be fantastic.
Take your vitamins.
What's that?
Take your vitamins.
Yeah, take your vitamins and get some sleep. Yes.